Now that we have learned about transistors and about the 6 basic Boolean operators, we're going to see if we can get transistors to replicate the Boolean operators. So each of the Boolean operators can be implemented as a digital circuit made of one or more transistors. These digital circuits are known as gates, and they are represented with graphical symbols. We're going to start with the first transistor and see if we can recognize through the truth table which one of the gates this represents. So let's try the first one. So this should look familiar to you. This is just a standard transistor. So once again, we're going to draw a truth table for it and see what we come up with. There is one single input and there is one single output. If I do not put a voltage on the input, that means that the current cannot pass to ground, therefore it must go to the output. But if I do put a current across the input, that means that allows the current to cross the gap and go to ground, and therefore it does not go to the output. So does this truth table look familiar to you based on the Boolean operators that we outlined earlier? This is actually a logical NOT. So the basic state of a transistor is a NOT gate. The symbol for a NOT gate looks a little bit like a triangle with a circle on the front of it. It has a single input into the gate and a single input or a single output out of the gate. So let's try another one. This time I'm going to take 2 transistors or 2 NOT gates and I'm going to put them in series. So let's draw the truth table and see if we can find out what this looks like. So as always, I'm going to start with no voltage across either one of the inputs. If there is no voltage across either one, that means the current will not be able to flow to ground, therefore it will have to go to the output. So let's put a current across the first input but not the second one. If I put a current across the first one, the voltage will be able to flow across the first transistor but not the second one, therefore it can't go to ground, it's still going to have to go to the output. So let's reverse it. If the current cannot cross the first transistor, it is still going to go to ground. And then finally I'm going to put a current across both of the transistors. This is going to allow the current to flow across both of the gaps and therefore it will go to ground, and if it goes to ground it will not go to the output. So does this particular truth table look familiar to you? This is actually the Nand gate. And the symbol for a Nand gate looks a little bit like a D. It has 2 inputs and it has a single output, but because it's the not AND, there is a circle on the front of it. This means that I can take 2 transistors or 2 NOT gates, and using those I can create a Nand gate. So let's try the next one. So we're going to start here. This should be familiar to you because this is our Nand gate that we just drew before. But instead of having it just as the output, this is actually going to be the input into another transistor. So now we have a second transistor that the output is going into. And let's see if we can come up with a truth table which is going to help us identify what this particular logic gate is representing. So this should look familiar to you, because this is a Nand gate. This should also look familiar to you because this is a standard transistor, which is a NOT gate. What do you think is going to happen when I pass the output from a Nand gate through a NOT gate? What would you expect to have happen? Well, we know if I put a 0, 0 into a Nand gate, I know that the output is going to be a 1. But the idea that I'm going to pass this 1 through a NOT gate is going to reverse it, and I'm going to get a 0. So if I put a 1, 0 through a Nand gate, the output is going to be a 1. But once again, if I pass a 1 through a NOT gate, this is going to give me a 0. If I put a 0, 1 through a Nand gate, once again the output is going to be a 1. And if I pass a 1 through a NOT gate, we know that it reverses the output, and this will give me a 0. And finally, if I pass a 1 and a 1 through a NAND gate, I know that the output gives me a 0. And when I pass a 0 as an output through a NOT gate, it is going to reverse that, and it's going to give me a 1. So does this particular output look familiar to us? This is actually an AND gate. And the symbol for an AND gate looks just like a NAND gate, with the exception that there is no circle on the front. There are two input into the NAND gate and a single output coming out of it. So let's try another one and see what we can get. Now I have two transistors, but this time instead of being in series, they're in parallel. And so I have the two, input 1 and input 2. I want you to notice that this symbol indicates the fact that this wire does not cross the wire. It kind of bridges it, because if it did cross it, it would create a short. So let's draw up a truth table for this and see if we can identify what it is. So if we put no voltage across either one of the transistors, then the current is not going to be able to cross either one to go to ground. Therefore, it has to go to output. If I put a voltage across the first one, but not a second one, that means that the current is going to be able to go to ground across the first one. And once again, if it can go to ground, it will not go to the output. So now let's put a current across the second one instead. And once again, if that current can cross that gap, it is going to go to ground instead of going to the output. So the output will be 0. And then if I put a current across both of them, then the current will be able to, the electricity will be able to go to ground on both sides. Therefore, the output will be 0. Does this particular truth table look familiar to you? It should, because this is the logical NOR, the not OR. The symbol for a logical NOR, there are two input coming into it, and there is a single input coming out, and it is a not OR, so I'm going to put the circle at the very first, the front of it. So now I have a NOT gate, and this is also a NOT gate. When I put two of them in parallel, I can create a NOR gate. So let's try another one and see if you can identify this one. So this should look very familiar to us because we just drew it. This is the NOR gate, but instead of stopping with the output, this is going to be the input into another transistor. So we're going to take the output from a NOR gate and we're going to pass it through a NOT gate, and we're going to see if we can find out what it's going to be. So let's draw a truth table. So if I have no voltage across either one of the inputs, a NOR gate would tell me that the output is a 1. But if I pass a 1 through the output, or if I pass a 1 into a NOT gate, it is going to reverse that output, and I am going to end up with a 0. So if I put a 0 and a 1 through a NOR gate, the output should give me a 0. But if I pass a 0 through a NOT gate, it will reverse that to a 1. So let's reverse that and put a 1, 0 through a NOR gate. The output should be a 0, but again, if I put a 0 as an input into a NOT gate, it will reverse that and give me a 1. And finally, if I pass two 1s through a NOR gate, it should allow the electricity to flow to ground. Therefore, the output is going to be a 0. And if I put a 0 through a NOT gate, it is going to reverse that to a 1. So, does this look familiar to you? This is an OR gate. And the symbol for an OR gate, there are two inputs, and there is a single output. So this is a NOR gate, and this is a NOT gate. And using one NOR gate and one NOT gate, we can create an OR. The last one that we're going to draw is an exclusive OR. And I'm going to draw it, instead of drawing transistors, I'm going to draw it as a series of gates. It is going to use two NOT gates, it's going to use two AND gates, and it's going to use one OR gate in order to create an exclusive OR. So we're going to start with two NOT gates, then we're going to add two AND gates, and we're going to end up with one OR gate. There'll be an input 1 and an input 2 into each one of the NOT gates. But the AND gates require 2 inputs. So I'm going to take an input from 1 and I am going to pass it into the AND gate. And I'm also going to take an input from 2 and I'm going to pass it into the second AND gate. And both of these AND gates are going to come into the OR gate. So we have 2 inputs that lead to a single output. This is an example of an exclusive OR. My apologies to the graphic artists in the room. I am not artistically inclined. So we've learned about 1 transistor and 6 Boolean operators, and we have been able to simulate all 6 of the basic Boolean operators using 1 or more transistors. This combination of gates allows the computer to do all of the things that it does, and each one of the gates in a circuit reacts in completely predictable ways. So remember, we're talking about 2.6 billion transistors on a quad-core chip. That means 2.6 billion of these gates, each one creating ones and zeros, using electricity in order to tell the computer how to do everything that it does. This is an amazing thing, and you should give your computer a hug and tell it how much you love it. The fact that it works at all is truly a miracle.